Welcome back. In this video, we're going to look at example problems of calculating the volume of solids with known cross-sections using definite integrals. Let's get to it. All right, so here's our first example. We want to find the volume of the solid whose base is the region bounded by y equals x squared, y equals 0, and x equals 4. The cross-sections of the solid that are perpendicular to the x-axis are isosceles triangles with a leg on the base of the solid. All right, and so the first thing that we should do here is draw a graph of our region that represents the base of our solid. And so I'll start by drawing the y-axis, and then I'll draw the x-axis, and then I'll label them. So this is the y-axis, and that's the x-axis. Okay, and so let's graph each of these functions. Let's start with y equals x squared. We know that x squared is a parabola that points upwards, and the vertex is at the origin. And so that will look something like this. That will be the parabola y equals x squared. And then we have y equals 0, which is just the x-axis, right? The x-axis is where y is equal to 0. And then we have x equals 4, which if this is x equals 4 along the x-axis, then this line right here will represent the line x equals 4. All right, and so now we can see that the region bounded by x squared, x equals 4, and the x-axis will be this region in here. And so I'll shade that in. This region represents the base of the solid that we want to calculate the volume of. All right, and so that solid has cross-sections perpendicular to the x-axis that are isosceles triangles. And the isosceles triangles have a leg on the base of the solid. And so let's draw a 3D representation of what that looks like. This is going to be a quick sketch. It's kind of hard to draw three-dimensional figures on a 2D surface, but I'll do my best here. This will be our y-axis, and this is our x-axis. Our parabola looks something like this, and so that is y equals x squared. And then let's say that this right here is x equals 4, right? So that will be x equals 4, which means that our region, that is the base of our solid, is this region right here. Okay, and so if our solid has cross-sections that are isosceles triangles that are perpendicular to the x-axis, then that will look something like this. All right, so we could draw a couple of these along our region, but you get the idea. Throughout this region, we will have these isosceles triangles where one of the legs lies along the base of the solid. Okay, so if I connected these points, you could start to see the shape of the solid formed, but it's important to note that each of these isosceles triangles has legs of equal length, right? That is what an isosceles triangle is it's a triangle that has two sides that are the same length. And so I label that with B. All right, and so if we want to calculate the volume of this solid formed by these triangular cross sections and this base, that is this shaded region, then we need to use the following formula for that volume. The volume will be equal to the definite integral from A to B of the cross-sectional area in terms of x times dx. Now I wrote this equation in terms of x because our cross-sections are perpendicular to the x-axis. If they were perpendicular to the y-axis, then we would be working in terms of y. And we'll look at that a little later, but for this example, we are working in terms of x. And so what we need to do here is determine the area of our cross-sections of our solid. And so in this case, since our cross-sections are isosceles triangles, the cross-sectional area in terms of x will be equal to the area of an isosceles triangle. And so a of x will be equal to 1/2 times b squared, right? That is going to be the area of this isosceles triangle. And so now what we need to do is determine what b is equal to. And notice that b is the length of one of the legs of our isosceles triangles, and one of those legs lies along the base of our solid. And so that distance, no matter where we are in our region, the leg of these triangles is equal to the distance between the x-axis and this curve y equals x squared. And so if we look at our graph over here, this distance right here is b, which is the length of one of the legs of our isosceles triangles. And so b will be equal to x squared. And so we will have that the cross-sectional area in terms of x is equal to 1/2 times the measurement of b, which we just said is x squared, squared. And so the cross-sectional area will be equal to 1/2 times x to the 4th power. All right, and so if we clean up our work here, we can now set up a definite integral to represent the volume of our solid in this example. We already determined the cross-sectional area Now we just need to determine our bounds of integration. And so our bounds of integration are going to be the values of x that our region lies between. And so if we look at our region here, it lies between x equals 0 and x equals 4. And so the volume will be equal to the integral from 0 to 4 of the cross-sectional area, which is 1/2 times x to the 4th power times dx. All right, and so now we have a definite integral that represents the volume of that solid that is pretty easy to solve. And so if we pull this 1/2 to the outside of the integral, this will be equal to 1/2 times the integral from 0 to 4 of x to the 4th power times dx. And now we can integrate this by using the power rule of integration by adding 1 to the exponent and dividing by that new exponent. And so we'll have that this is equal to 1/2 times x to the 5th power divided by 5 evaluated from 0 to 4. And so if we clean up our work here, we can evaluate this expression at 4 and subtract the evaluation at 0. And so this will be equal to 1/2 times 4 to the 5th power divided by 5 minus 0 to the 5th power divided by 5. And that will be equal to 1/2 times 4 to the 5th power, which is 1024 divided by 5 minus 0. And so that will be equal to 1/2 of 1024 divided by 5, which is equal to 512 fifths. And so that is the volume of our solid that has this region as its base and cross-sections that are isosceles triangles perpendicular to the x-axis. So here's our next example. We want to find the volume of the solid whose base is the region bounded by the circle x squared plus y squared equals 1. The cross-sections of the solid that are perpendicular to the y-axis are squares. All right, so let's start this problem by drawing our region that represents the base of our solid. In this case, it's bounded by one single equation, this equation right here, which is a circle. And so let's graph that. Here's the y-axis, and then here's the x-axis, and then I'll label them. So this is the y, and this is the x. All right, and then let's graph our circle. This is the general form for an equation of a circle, at least for one that is centered at the origin. And so whatever x squared plus y squared is equal to, the square root of that value will be the radius of that circle. And so the square root of 1 is just 1. And so we know that the graph of this equation will be a circle with a radius of 1. And so if this is x equals 1, this is y equals 1, this is x equals -1, and this is y equals -1, then our circle will look something like this. All right, and so this circle bounds the entire region that represents the base of our solid. And so I'll shade that in really quickly, although it's pretty obvious what our region is in this case. You might not necessarily have to shade it in, but I'm going to do it anyway. Okay, and then just as a reminder, this circle is x squared plus y squared equals 1. And so this solid has a base that is a circle, but its cross-sections that are perpendicular to the y-axis are squares. And so let's draw a quick sketch of what that would look like in 3 dimensions. And so if this is our x-axis and this is our y-axis, and I'll label them really quick. Here is the y-axis and there's the x-axis. Our circle would look something like that, and our cross-sections that are squares will look something like this. And we can continue to draw more and more of these squares that together would form the solid that we are calculating the volume of. Okay, and so now since these square cross-sections are perpendicular to the y-axis, we are going to be setting up a definite integral in terms of y. And so that will look like this. We'll have that the volume is equal to the definite integral from c to d of the cross-sectional area in terms of y times dy. Now the cross-sectional area in this case is going to be the area of a square. And we know that the area of a square is equal to the length of one of its sides squared. And so in this case, we need to determine what the length of one of the sides of these squares is. And so if we look at the bottom of each of the squares, notice that their side is going to be equal to the distance from one end of the circle to the other end of the circle. And so in order to express that distance in terms of y, we're going to need to rewrite our equation for a circle in terms of y. And so what we need to do is solve for x in this equation. All right, but just remember that the distance from one end of the circle to the other is the length of s, or one side, of our squares. And so if we clean up our work here, let's solve for x in this equation. We currently have x squared plus y squared is equal to 1. If we subtract y squared from both sides of the equation, we will have x squared is equal to 1 minus y squared. And then if we take the square root of both sides, we will have that x is equal to plus or minus the square root of 1 minus y squared. Okay, and so the positive square root of 1 minus y squared will represent this half of the circle for the positive values of x, and the negative square root of 1 minus y squared will be this side of the circle for the negative values of x. Okay, and so if we want to know what s is equal to, we can subtract the lower boundary, or the lower half of the circle, from the upper boundary, or the upper half of the circle. Okay, so we would say that s is equal to the positive square root of 1 minus y squared minus the negative square root of 1 minus y squared. Right, the positive square root of 1 minus y squared is this half of the circle, and the negative square root of 1 minus y squared is this half of the circle. And so we subtract the left side from the right side, and that will give us the distance between those two sides. And so s is equal to the square root of 1 minus y squared plus the square root of 1 minus y squared, because these two negatives will cancel out to become positive, and so then s will be equal to 2 times the square root of 1 minus y squared, right? These are the same expression, and so we can combine them to be 2 times the square root of 1 minus y squared. All right, and so that is the length of one side of the square, but if we want to determine the cross-sectional area, we need to plug this in for s in this equation. And so if I erase this work right here, we will have that the cross-sectional area in terms of y is equal to 2 times the square root of 1 minus y squared squared. And so if we simplify that, the cross-sectional area will be equal to 4 times 1 minus y squared. Right, we just squared each of these factors, so 2 squared is 4, and if you square a square root, you're just left with what is inside, and so we have 4 times 1 minus y squared. Okay, and so now that we know what the cross-sectional area is equal to, we can use that to set up our definite integral to calculate the volume of our solid in this problem. And so let's clean up our work again. We will have that the volume is equal to the definite integral from c to d, which are two values of y. So what values of y does our region lie between? Well, it lies between y equals -1 and y equals +1. And so our bounds will be from -1 to +1. And then our cross-sectional area in terms of y is 4 times 1 minus y squared. And so we will have 4 times 1 minus y squared times dy. Okay, and so this definite integral represents the volume of our solid in this problem. And so now all we have to do is solve it. And so if we pull this 4 to the outside of the integral, this will be equal to 4 times the integral from -1 to 1 of 1 minus y squared times dy. And now we can integrate each of these terms. So we'll have that this is equal to 4 times y minus y cubed divided by 3. And that is evaluated from -1 to 1. Right, so the integral of 1, or any constant, is just that constant times the variable of integration, which in this case is y, and so the integral of 1 is y, and then we integrated y squared by using the power rule of integration by adding 1 to the exponent and then dividing by that new exponent. Okay, and so if we clean up our work here, we can plug 1 into this expression and then subtract plugging -1 into this expression. So we will have that this is equal to 4 times 1 minus 1 cubed divided by 3 minus -1 minus -1 cubed divided by 3. All right, and that will be equal to 4 times 1 minus 1/3 minus -1 minus -1 divided by 3. Right, -1 cubed is just equal to -1, and so we have -1/3. Now these two negatives will cancel out to become positive, and so we will have -1 plus 1/3, so I'll write that as a plus. And now if we clean up our work again, we can simplify, and this will be equal to 4 times 1 minus 1/3, that's equal to 2/3, minus -1 plus 1/3, which is equal to -2/3. All right, and then 2/3 minus -2/3 is the same as 2/3 plus 2/3, and so this is equal to 4 times 4/3, which is equal to 16/3. And so 16/3 is the volume of the solid that has a circular base and cross-sections that are squares that are perpendicular to the y-axis. All right, let's look at one more example for this video. All right, so here's our last example. We want to find the volume of the solid whose base is the region bounded by y equals x plus 1 and y equals x squared minus 1. The cross-sections of the solid that are perpendicular to the x-axis are rectangles with a height of 3. All right, so once again, let's start by drawing the region that represents the base of our solid. So I will draw the y-axis, and then I'll draw the x-axis, and then I'll label them. So there's the y, and here's the x. And then let's start by graphing y equals x plus 1. And y equals x is just a line that crosses through the origin with a slope of 1, and then this plus 1 tells us to shift it up 1 unit in the y direction. And so if this is y equals 1, then our line will look something like this. Okay, so that is y equals x plus 1. And then we have y equals x squared minus 1. And y equals x squared is a parabola that points upwards where the vertex is at the origin. But this minus 1 tells us to shift that down 1 unit in the y direction. And so the vertex won't be at the origin, it will be at 0, -1. And so that parabola will look something like this. All right, so that is y equals x squared minus 1. And so the region bounded by these two functions, or this curve and this line, will be this region right here. And so I'll shade that in. This region represents the base of the solid that we want to calculate the volume of. And so now this solid has cross sections perpendicular to the x-axis that are rectangles with a height of 3. And so let's draw a 3D sketch of what this solid would look like. And remember that this is just a sketch, so it's not going to be perfect, but here's our y-axis and our x-axis. All right, and then I'll label them. So this is the y-axis, and this is the x-axis. And so then if our parabola looks like this, that's going to be y equals x squared minus 1. Then our line will look something like that. Again, this is not a perfect drawing, but that's going to represent y equals x plus 1. Okay, so this will be our shaded region that represents the base of our solid. And so if our cross sections that are perpendicular to the x-axis are rectangles with a height of 3, here is what those cross sections would look like. We could have one right here that will look something like this, and then we could have another one that will be the same height, that height of 3, and then we could have another one that will still have that same height, and then we can have one more over here that would also have that height. Now we can continue to draw more and more of these cross sections throughout this entire region, but hopefully you can see that together all of those cross sections would form a 3-dimensional solid where this shaded region is the base. Okay, so this height right here of each of those rectangles is equal to 3, right? That is the height of each and every one of those rectangular cross sections. And so if we're going to determine the volume of this solid, we're going to be working in terms of x because our cross sections are perpendicular to the x-axis. And so we will be using the formula that the volume is equal to the definite integral from a to b, where a and b are values of x, of the cross-sectional area in terms of x times dx. Now in this case, the cross-sectional area is going to be the area of a rectangle, and the area of a rectangle is equal to the height of the rectangle times the length of one of the sides of that rectangle. And so the length of one of the sides is going to be this length right here that is along the base of our solid, right? We already know what the height of our rectangles are. That was given to us in our problem. They all have a height of 3, but we need to determine what S is, or the side of our rectangles that lies along the base of our solid. And so notice that the length of those sides is equal to the distance between these two functions, the parabola and this line. And so if we look over to our graph over here, that measurement of the side is this distance right here. That is going to be S for our rectangles. And so it doesn't matter where we are in this region, that distance is going to be equal to this line, x plus 1, minus this parabola, x squared minus 1. Okay, and so if we clean up our work here, we have determined that the cross-sectional area will be equal to the height of our rectangles, which is 3, times S, the side length of our rectangles, which is equal to this line minus this parabola. And so we will have x plus 1 minus x squared minus 1. And remember those parentheses because this negative is going to affect both of those terms. All right, and so this right here is S, the side of our rectangles. And so let's simplify. This will be equal to 3 times x plus 1 minus x squared plus 1, which if we combine these two ones will be equal to 2. And so what we'll have is that this is equal to 3 times x minus x squared plus 2. All right, and so that is the cross-sectional area, a of x, for our definite integral. And so now all we have to determine is our bounds of integration. And those are just going to be the two values of x for which our region lies between. And so if we look at our region here, we actually don't know what the two values of x are that it lies between. We know it lies between where these functions intersect, but we need to determine what those values of x are, where those functions do intersect. And so in order to figure that out, we need to set our functions equal to each other and then solve for x. And so if we clean up our work here, let's set our two functions equal to each other. We will have that x squared minus 1 is equal to x plus 1. And now we want to solve for x so that we can figure out the values of x of the intersection points for these two functions. And so if we subtract 1 and subtract x from both sides of the equation, we will have x squared minus x minus 2 is equal to 0. And so now we have a quadratic that we can factor, and the factorization of that will be x minus 2 times x plus 1, and that will be equal to 0. And the way you determine this is if the first term of your quadratic has a coefficient of 1, then you can look at your last term and ask yourself what two factors of that term, when added together, equal the coefficient of the middle term. And so in this case, for negative 2 times positive 1 is negative 2, and then negative 2 plus positive 1 is negative 1. And so those are going to be our factors of that quadratic. And so, if we set each of these factors equal to 0, we will have x minus 2 is equal to 0 and x plus 1 equals 0, which gives us that x equals 2 and x equals negative 1. And so now we know that the x values of our points of intersection are negative 1 and positive 2. And so that means that this is probably negative 1 right here, and this is probably positive 2. And so our region lies between x equals negative 1 and x equals positive 2. All right, and so now we can set up our definite integral. And so let me erase this work, and we will have that the volume is equal to the definite integral from negative 1 to 2 of our cross-sectional area, which is this right here, 3 times x minus x squared plus 2 times dx. Okay, and so if we pull this 3 to the outside of the integral, we'll have that that is equal to 3 times the integral from negative 1 to 2 of x minus x squared plus 2 times dx. All right, and so now if we clean up our work, we can integrate each of these terms, and we'll have that the volume is equal to 3 times x squared divided by 2 minus x cubed divided by 3 plus 2x, and that is evaluated from negative 1 to 2. All right, so we just used the power rule of integration on each of these terms, and the integral of 2, which is a constant, is just that constant multiplied by the variable of integration, so we have 2x. Okay, and so now we'll evaluate this at 2, and then subtract the evaluation at negative 1. And so this will be equal to 3 times 2 squared divided by 2 minus 2 cubed divided by 3 plus 2 times 2 minus negative 1 squared divided by 2 minus negative 1 cubed divided by 3 plus 2 times negative 1. All right, and so if we simplify, this is equal to 3 times 4 divided by 2 minus 8 divided by 3 plus 4 minus 1/2 minus negative 1 divided by 3 minus 2. All right, and that will be equal to 3 times 2 minus 8/3 plus 4 minus 1/2 plus 1/3 minus 2. Okay, so 4 divided by 2 is equal to 2, and then these two negatives became positive. All right, and so let's clean up our work here one more time. This will be equal to 3 times 2 plus 4 is 6, so we'll have 6 minus 8/3, and then we will subtract 1/2 plus 1/3. That's equal to 5/6 if you were to get a common denominator on both of those fractions, and then add their numerators, and then we still have minus 2. And 6 can be rewritten to be 18/3 because 18 divided by 3 would be 6. And so 18/3 minus 8/3 would be 10/3. And so this is equal to 3 times 10/3 minus 5/6 minus 2. And 2 would be 12/6. And so 5 minus 12 is negative 7. And so we have negative 7/6. And then that will be equal to 3 times 10/3 plus 7/6. And 10/3 would be equal to 26. And so 26 plus 7/6 would be equal to 27/6. And so we have that this is equal to 3 times 27/6. And 27 divided by 6 reduces to 9/2. And so this is equal to 3 times 9/2, which is equal to 27 divided by 2, or 27/2, And that is the volume of the solid that has this region as its base and cross-sections perpendicular to the x-axis that are rectangles with a height of 3. Okay, and so with that, that is it for this example, and this was the last example for this video. And so if you have any questions, feel free to leave those in the comments, but if you don't have any questions, this is all I had for now, so I will see you next time.